Welcome back to the course. In this lesson, we'll be talking about buffer overflows. The main memory, or random access memory RAM, of your computer stores data and lines of code to be executed on a CPU. The main memory is divided into distinct areas dedicated to storing things such as code, user input, local variables, and return addresses. Especially the area of your memory storing user inputs is referred to as buffer, and the buffer we're talking about in buffer overflows refers to this area of main memory. Return addresses are 4, indicating the next line of code to be executed on a CPU. We can think of these different areas of your main memory as bit buckets, and especially when the area of your main memory storing user inputs called buffer gets overflowed by excessive user inputs, it can contaminate the other areas of your main memory or bit buckets, like this. So for example, if the buffer contaminates the code area of your main memory, somehow your code gets corrupted, or the information inside the buffer overflows into the bit bucket storing local variables, the local variable information can be corrupted. The information inside the buffer can also overflow into the return address section of your main memory, again corrupting the information in the bit bucket. So the program running on your computer now doesn't know what to execute next. In reality, the organization of your main memory looks like this. It consists of heap, stack, and areas storing global data and program instructions. A stack is a scratch space reserved for a thread of execution. For example, when you're executing a function, you need a temporary space to store information about the function while it is running. Some of the information you need to store about the function includes return address, local variables, and parameters. The return address is for the address of the code to be executed when the function is done executing. We use the term frame when we're talking about a stack, and a frame refers to a unit of a stack space, and it gets created whenever, for example, a function call is made. There is one frame created for that particular function call. If there's another function call, another frame gets created, and so on. The frames are added to the memory in a Phyllo fashion or Phyllo fashion. Phyllo stands for first in, last out. And what this means is that whenever there is a new frame added to the memory, it will be added to the end of the existing frame, and then when it's time for us to somehow remove the frame, the last frame added to the memory will be removed first, and then the very first frame that was added to the memory will be removed last. So that's really the nature of a stack, how it operates. There are also some terms you should be familiar with. In this case, a frame pointer refers to the address of the beginning of a stack frame, as you can see here. And then the stack pointer, in this case, refers to the address of the top of the stack frame. And here, this is a little counterintuitive, but when we're describing a frame in a stack, we say that the stack is growing downwards like this, and every time a new frame is added to the memory, it's going to be added to the top of the last frame like this. A heap is memory set aside for dynamic allocations when you're writing your code. For example, when you write a piece of code like box star space p underscore bar equal sign new space box open angle bracket 4 close angle bracket and semicolon. What this means is simply create 4 spaces in your memory for this class called box, and this dynamically allocated memory spaces will be placed in a location of your memory called heap. So if we go back to our reality slide, as you can see, the heap grows upwards while stack grows downwards, and other pieces of information in your memory such as global data and program instructions are well away from the stack. However, if you have a lot of information added to the stack, it will eventually override, for example, some areas of your memory. There are some serious consequences that could result from stack overflows. For example, your program can simply crash if somehow the stack overflow overrides a portion of your program instructions. Another consequence is a little more sophisticated and also subtle, because without really somehow making it obvious to the users of the program, these attackers can somehow secretly execute a malicious piece of code behind the scene. So this is even more dangerous. To avoid this type of undesirable situations, we can use some countermeasures. Of course, the best thing is always prevention, and I recommend you use secure coding practice when you write your code. Some of these secure coding practices include things such as input validation, using safe function calls, and enabling compiler warning features and paying attention to them. And there are some hardware solutions too. So, for example, there's something called stack execution invalidation, which means your memory somehow detects a piece of code trying to be executed in your stack area, and then it automatically disables the execution of a piece of code in your stack space. In our course, our focus is secure coding, so we'll be discussing input validation and safe function calls definitely in more detail. If you are listening to my lecture carefully, you should be able to answer this question very easily. Is it possible to execute malicious code through a buffer overflow attack? What is your answer? Is it true or false? The clock is ticking. Did you have fun? The next topic we'll be covering is SQL injection.